So for today, we'll discuss edge computing, key components, challenges and limitations, and basically some similarities between cloud and edge. And then, of course, we want to understand also their difference. And lastly, we'll have some summary of key learning points. And this is a bit, one of our short courses in Asia Open RAN, but it's technology that is being deployed as we speak, and not a lot of people knows about edge computing since we're still in the cloud high era. So what really is edge computing? And when we're talking about the edge, it's really just a distributed computing paradigm. So it makes processing and storage of data instantaneous by bringing this computing system as close as possible to the device, application, or component that collects and generates this data. So advantages: better control over data, reduce cost, provides faster insights and action, enable very streamlined operations when deploying edge computing as compared to just pure traditional cloud computing. Okay. So here's an example of what edge computing looks like from Spice Networks. You still have your cloud and data center, no? But typically you'll have your edge computing platform with the edge gateways somewhere in the middle as intermediary, but it's going to be as close to the device, edge devices or IoT. And some of it actually are embedded within the edge device itself. No? So that also helps with processing. So history, where did this came from? So it was roughly based on the content distribution network that was developed in the 1990s to serve videos and other contents and even just pictures, across the internet, where uh, people realized that a single server or even a cluster of servers most likely would not be able to serve the required consumption of end users, in the early days of the internet. So just imagine, let's say, the Google logo not being displayed on the Google search engine. Most likely on the initial design, they are honing to one single server, eventually a cluster. Try to imagine 10,000, 100,000 of people, especially with the .NET boom, trying to grab that picture. Your computing capacity might be able to scale, with that request, but maybe your bandwidth, or even your data center, might not be able to perform, the required throughput, to serve all of those users. Since they started developing the concept of why would we host it on one central location? Why couldn't we just distribute it, across multiple hosting across the globe, and people with the nearest source, it's where the people would get that image, making it more efficient, not bombarding the data center with just requesting a single image, and have our compute node, on that central location perform what's intended to do, like central data processing and everything, but all the rest of the support images or resource, could be distributed outside. So this basically this CDN, um in the 2000s, this evolved into hosting apps on the edge servers to develop the earliest form of commercial edge computing. And for those of you who haven't discovered how a CDN works, it's as I described a while ago. No? So you'll still have a central location or the origin server that's going to be distributing the content to the edge servers. And wherever your user is nearer, it depends. It's either via routing or via DNS. The system is going to direct you to the nearest edge server. And this is typically how, in a sense, Netflix work. They would have, well, they are a movie producing or a video content distributor, right? So if they put their movie on a central location, let's say on a server somewhere in US, okay, you cannot expect all the users of Netflix to connect to that source and have them all download that movie at the same time. So that's not gonna scale. No, ultimately the bandwidth to the US continent's gonna get bogged down. So what they designed was, well, I'll have still no, the sign up, the display, the searching. They're still hosting it in AWS. But what they did was they contracted these telcos that, well, if you want to offer Netflix, we would be sending to you an edge server that's basically gonna cache all the recent content, and based on their analytics, all the content that would be high in demand, even depending on the time of day. Because ultimately, these edge servers would have limited capacity, right? But they have good prediction algorithm that, okay, it's nighttime, most likely people at home's gonna need to watch or want to watch Korean novela. So they're gonna preload all those maybe full series if they're gonna binge watch no these Korean novelas on the edge servers, or if they're gonna be releasing a highly anticipated movie of maybe Chris Hemsworth maybe a few hours before the release, no, they're gonna be preceding this on the edge server. So by the time that when the users no or this movie gets officially released, you won't have to go through the central server. You'll just be connecting to your edge server and gonna be downloading the content from there. And on this sense, let's say on the Netflix deployment of the CDN, no, you're not even gonna go out of your network, hence saving the network bandwidth. No. Just imagine, let's say you're Globe or Smart, and your users are downloading Netflix videos live on the network. I'm sure the capacity would be greatly affected. You might not back down, but a huge content of the utilization would be Netflix. And similar case, since YouTube is also a huge traffic consumer in our in bandwidth. Let's say when doing analytics in UP, maybe I would say 70-80% of the bandwidth is YouTube. We have edge servers or Google Cache servers, at least on our end, hosted in DOST ASTI, and it's within our local research network. So we don't have to go out of the internet to get cached YouTube content. So on the event that you request, let's say, a movie that was popular 2 years ago, but for some reason you have a lot of backlog and you just want to watch it now, your browser would or your app, no, web application would maybe attempt to talk to the edge server and determine that, oops, the content is not there. So two things could happen. It's either you will be directed to the next edge server, someone close that has that content, or maybe the edge server would be requesting it no, from the origin server, and then have you wait a bit, or what you call buffering, for you to be able to serve it to you. Because on some instances, you might not be the only one that's gonna watch that. There might be a trigger, maybe a viral social media snippets no, that pique your interest on that movie. So what happen is maybe a lot of people soon no, would be watching that movie. So the system would know that that is a possibility. So it's gonna push that content to the edge server. So that the second person who would request that movie, they would find that content no, cached on the edge server. So that's in theory no, how CDN work, and that's how roughly also edge computing work. No? So I got this little skit here no? Where um, if you remember in the 70s, if you're alive by then, right? Not be all of us, no? I'm not, we're doing it in the 70s, but um, in the early days of computing, 60s, 70s, no, everything is centralized. So you could consider that as the early form of cloud. You have your mainframe, you have your terminals accessing that mainframe. Um, and then here comes Bill Gates with Microsoft DOS and with the concept of a computer in every home. Now, it might be being laughed at that time, no? But well, a few years after, no, it became a reality. No? Each and every family has computers, and now, no, with mobile technology, um, maybe not that far off to assume. No? You maybe have at least 10 IP addresses in your home, host with IP addresses in your home. You got multiple phones, you have your tablet, you have multiple laptops, you have your TV and IoTs. No? So, but there was a time that everyone was having their own computer at home, and you could think of it as, well, it's a distributed computing environment, no? But it's contained, no? Self-contained. And then came the internet. So everyone's trying to connect, but and people realize now, okay, maybe we need some sort of a server. So try to centralize it a bit. No? And then came the cloud. So the cloud attempts, well, in theory, no, it's just uh, a computer in a data center. No? So that's you subscribe to. So you had this concept of moving our data to the cloud. And yeah, a lot of people were high and mighty that, yeah, let's move our applications to the cloud. And you don't need that server anymore, no? In the data center. So everyone, and most likely a lot of you guys, try to move to the cloud. And the pandemic actually helped, no, boost the cloud. Because I'm not sure if you are doing purchasing of hardware at that time. Um, it became a pain, because a lot of manufacturers have reduced capacity. Some even stopped production during the pandemic. I remember ordering aisle, no, of data center equipment, and the lead time that the vendor was giving me was at least 180 days. And that's non-committal, no? So almost 6 months to a year of waiting time for those equipment to arrive. And a lot of people have, of course, this bright idea they want to deploy something, no? And they cannot buy the hardware. Even if they have money, they cannot. It's impossible to buy hardware. Hence, cloud computing became, if you're not gonna allow us to buy hardware anyway, no, maybe we could go with an OpEx approach, no? Sign up in AWS, sign up in Google Cloud, sign up in Azure, instantiate our EC2 instance, or compute instance, and then be done with it. And you also have the benefit of not paying upfront, no? With cloud computing. Okay, and it's pay as you use. If you're not using a server, you could power it down, and you're gonna be charged with some uh, very basic charges on storage, no? And you could even scale, no? If at some time you have demand, no, for your app, you could do auto scaling, and you would still be able to service that um, request, or that peak, no? And your users won't even notice the difference, no? And when the demand decreases, you could just scale it down. Now, the problem is there are still some issues with cloud computing that unfortunately cannot be solved. No? Like one thing that's very prevalent with cloud computing, especially with our current infrastructure, latency. It's uh, it's physics. No? Ultimately, you're limited with the speed of light. But even then, there's still latency on how much time, no, your data would your request even, would travel from your compute device to the cloud and then back. So there are some instances where that might not be warranted. You want very low latency and high responsive systems. No? So sometime later, you got that. Now you need this brand new edge server. So there's now a move to install a server back in our environment. Hence that sort of a joke here. So why edge computing? So this endpoints, no, they generate a lot of data, and they send this to a centralized platform, no, either an internal server or cloud environment, through the network, either via LAN or WAN, maybe both, no. And this central platform, no, crunches the data and sends this back to the endpoint. Now you see the problem there. You are putting, in theory, no, all your eggs in one basket. While cloud could scale, no, you might not have the credit card limit, no, to fund that. So while it could definitely scale, your limit is the amount of cash you have, no, allocated for your cloud computing. There's also volume. No? I'm not sure if you have encountered cloud migration that they just initial computation was how much would EC2 instance cost? It's cheap, right? If you factor in the hardware cost, the maintenance cost, the cooling, the power, even the space, no, to host the server. But a lot of the computations that I've seen, no, when doing cloud migration lacks the consideration for bandwidth. And with bandwidth, it's not just the capacity, no, diba? For all we know, you have a 1 terabit per second link, no? Not 1 terabit, 1 terabit link, no? But the latency is uh 5 minutes. So 1 terabit per 5 minutes. No? So it doesn't make sense. No? It's gonna be very very slow. And if you have dabbled into TCP/IP, you know that the response time or the network latency plays a huge factor in bandwidth, no? Or the amount of data that could actually be pushed through the pipe, because it's doing an acknowledgement. If the acknowledgement uh, is delayed, no? Or has some latency, even though you have the capacity, you won't be able to just pump the data into that pipe. So um, those are the few issues of uh, edge computing that cloud computing that edge computing is trying to solve. So key components. For this, we have data flows, no? From edge devices to the edge gateway, then to the edge data center, and likely centralized cloud. Most likely, you still have a cloud component, and that's basically the one that's orchestrating it all. Like in the Netflix deployment, no? They are hosted, hopefully still in AWS, but that's just for sign up, no, and their search engine and for accounts management. But their source, no, they definitely wouldn't want to host it on AWS because that's gonna be very costly for them, no, storage wise and bandwidth wise. Hence, they use, no, a content delivery network, or could say it's a form of edge computing. So data is processed and analyzed on various stages of this path, no? Depending on the requirement of the application and use case. So what edge computing want to do is distribute the approach, no? And this in turn would reduce latency, improve data privacy and security to a degree, and make efficient use, no, of network bandwidth, because now you don't have to uh, push all the data generated to the cloud. And let's say on some remote instances where this edge and IoT devices are on environment, no, that is low power, low bandwidth, you most likely won't really be able to send that data anyway to the cloud um, in in a in a timely manner. So edge devices, these are IoTs or sensors, no, that produce, collect, and process data locally. And these devices can be anything. Smartphones, well, it is an edge computing device. And it's especially the flagship smartphones, no? They are more powerful than our laptops and workstations. Uh, Maybe 10 years back, maybe even as recent as 5 years back. No? It's very expensive too. You could see flagship phone that costs sometimes more, no, than your typical laptop cost. No? um, get smartphones, laptops, cameras, industrial equipment, such as robots, drones, and autonomous vehicles. No? They have this compute capacity built in with them. No? Um, they have initially, no, built-in processing power. They could enable performance of basic data analysis and filtering, no? And send, no, maybe just some big trigger data to the next stage, no, for edge computing architecture, no? So this helps reduce the amount of data transmitted and minimize latency. So let's say you have a camera IoT that tries to identify people without compute capacity within the camera or near the camera itself. Um, the basic setup would be that camera would send something and stream all those data back to DVR, and the DVR would have a compute power, no, to analyze frame per frame. Is there a person? Is there an object missing? Okay, and but now try imagine doing that computing and analysis for, let's say, 10,000 cameras. So how big of a cluster would you need to do that type of analysis? No? It's not going to be scalable. So what they thought was, well, if we could in capability, some ample storage, no, detecting, no, or alerting, if there is a missing object or is there a person, no, we might be able to reduce the bandwidth. No? Let's say you have 10,000 cameras for security surveillance. So what's gonna happen now is the camera is not gonna stream that data back centrally, or they could still stream it just for storage. No, but the analytics is perfect from the camera itself. When it detects with some basic machine learning that a person pop up, no, on this camera, target to edge gateways or eventually leads to the cloud, and then now you centrally, no, you'll have an alert that yeah, a person is detected on this camera, and your system will not have to process that centrally. It's part of the power that's imputed on the camera because you have it's basically an edge computing device. And again, you reduce the amount of data transmitted or processed on that sense. So it depends on the use case. Now you have the edge gateway. These are intermediary. No, you might, to some degree, no, that 10,000 cameras you might need really to still, no, store that video stream, but you might not want to send all those 10,000 streams to the cloud. So maybe per location you have this intermediary edge gateway that could act maybe as a digital video recorder. So your camera senses because they have compute power, but they still need to save the stream. Your edge gateways would take care of that for you. So this, they could do aggregation, storage. They could even, if the camera does not have the compute power, no, they could localize the processing. Have the camera stream at the edge gateway. Edge gateway would process maybe 100, 200 cameras. No? And then the edge gateway would be the one doing the alert and sending that data back to the central location or the cloud. So again, this ensures efficiency of your deployment. We could also handle protocol translation, data caching if you need to push some data back to the edge devices, and of course, security features and local storage. They may also host edge applications that require more compute resource than available on the edge devices themselves. So they could be working hand in hand. So while let's say the camera could process maybe 5 frames per second, no? Assuming that's the capacity, they could trigger on a BC camera or a BC scene. It might request the help, no? As long as you design their system that way, that yeah, I cannot process this anymore. There's a lot of movement, so I'll tap, no, the edge gateways to say that yeah, I'm not gonna process it. It's too many. Please use your compute power to analyze this stream. So you could hand off that processing to the gateways. Now, ultimately, they would have to be centrally correlated and orchestrated at some point. No? So we have what we call small edge data centers, but sometimes it's already hosted in the cloud anyway. No? Where you are, no? Trying to bring a better, no, or a larger compute and data storage after the edge gateway, no, to the edge data centers. But again, some of this, and I think most of this implementation is already in the cloud too. Very seldom would I see edge data centers that's not hosted in the cloud anyway. So, but ultimately, if you want latency still, reduced latency still, you would want this to be near um, your edge gateways, no, as near as possible, of course, to the end edge devices. Because for let's say uh, a network challenged country, no, like Philippines, latency wise, no, let's say for AWS, we don't really have an official data center here. We do have lease lines, no, direct to AWS, but if you're gonna host your system now on AWS, it's most likely gonna be hosted outside the country. So again, physics. Each time you, even on fiber optic connections, submarine cable adds significant latency, especially if you need near real time responsiveness. No? So that's maybe our local telcos, no, would come into play where they could host this edge data center for reduce latency communication between the edge data center to the edge gateway to the edge devices. And of course, we still can't eliminate the cloud. It's here to stay for quite some time. So this is the remote, very large scale cloud infrastructure that could provide no, additional processing power and storage capacity if needed, but it could only handle tasks that are not time sensitive no, or require more resource that's available on the edge gateway, and edge data center. So if you have a backlog of processing, then maybe the edge data center could offload that here. Or you have all this data set, you want to make some sense out of it using big data analytics or whatever new buzzword now we have in IT, process it there. But again, this is for mainly for non-time sensitive no, because of latency and cost. Sometimes you could have processing power at the cheap, but you have to do reserve instances and the likes, no? And you would mix and match allocation on what they're processing depending on your use case. So that is a factor to consider. And lastly, of course, we have that infrastructure. You have your edge analytics and application. So this is what system or processing that you want done in your uh, system, and making use of edge computing and uh, all of various key components. No? So the goal ultimately for edge computing is have data processed and analyzed in real time or near real time. Hence, the good um, link no, with Open RAN, since you need a lot of these components in Open RAN to be able to respond immediately, especially for a high bandwidth application. We typically want this system to be able to orchestrate themselves. No? And yeah, you got edge application software programs runs on the edge devices, gateways, or data centers. No? Performing various specific tasks depending on where they are and what you are after. No? Let's say for cameras on the camera use case, no? Camera would be processing any individual or person that's gonna be show up. You might not even be attempting no, to process that and identify that individual, but the camera is just detecting if there's a person in the scene. But that trigger could send, let's say, a JPEG no, to uh, up to the cloud. The video stream could be stored on the edge gateway, on eventually the edge data center for retrieval in the future. But that photo, maybe you could pass it to the cloud and have your um, biometric search no, based on facial recognition, perform an identification of that individual that was sent no, via a camera that was triggered that because of a person detection rule. No? And now, instead of your cloud processing and receiving all these 10,000 camera data and try to analyze, is there a person here? If there's a person, I'm going to pass it to the next workload to identify that individual. The cloud would be sitting pretty and just waiting for an alert with a JPEG. And then now it's going to perform their identification centrally. Because, well, central identification for biometrics or facial recognition, typically it runs on a very large data set, and it needs a lot of compute power, really. So you don't expect your edge devices to do that. Well, to some degree, maybe your edge data center could be able to do that, but maybe you have some restrictions. Now you cannot distribute that data set no, to edge data center, but you could host it in the cloud because of regulatory restrictions or maybe just compute capacity and storage capacity considerations. No? So that could be one of the use cases that for you to uh, check no, how edge computing is actually working. So challenges and limitations. No? Challenges is, well, again, edge devices are typically small ones. No? They have limited computing power and storage as compared to the current technology. No? So if you could just, well, see no, a Raspberry Pi 5 that has 8 gigabytes of RAM with gigabit connectivity that could display two 4K full-size resolution monitor that runs on a USB powered charger. No? You could still consider that limited, no, as compared to, let's say, a MacBook Pro M3 with 128 gigs of RAM. No, but if you consider a Raspberry Pi 5 to our compute capacity 10 years ago, that's actually a lot better. No? But ultimately, edge devices would be using this limited computing and storage equipment as compared to what we have in the gateways, data centers, and eventually the cloud. Uh, while to some degree there's an enhanced security with edge computing, there's also a security concern because if your devices, your edge devices is storing this configuration, this data locally, if it gets stolen, then well, data is there. Or if someone would be able to tap into the network communication from your edge devices to the edge gateways or maybe the cloud, they might see access tokens, credentials, configurations, or even just basic connectivity and routing rules. So that is exposure. That's a security concern. There's also the infrastructure and deployment cost because, well, edge computing devices typically it's more expensive than just dumb IoTs, because well, it did put additional compute and storage requirement there. There's also interoperability and standardization. Let's say, again, on the camera use case, you have 10,000 cameras, but no single vendor would be able to provide you with that single model to be deployed. Or maybe initially they would be able to do that. But if you're, let's say, running an operation for the next 10 years, some of those cameras would die. So you might need to be able to purchase and install a different model or worse, a different brand, and hopefully they work as intended and according to spec. But for those of you who have deployed this various network equipments in the past, you hopefully you could relate that when two vendors say that they have spanning tree protocol standard capability, but if you link them up, make a loop, and hope and pray that your spanning tree would kick in, sometimes you still have broadcast storm because the spanning tree did not kick in as intended because vendor A spanning tree is a different implementation from vendor B. But they say they are standard, which ideally should have worked as intended, but we all know that's not how it works in the real world. Also, issue with network connectivity. Again, edge devices, limited power. Typically, you have low bandwidth, short throw connectivity. Um, so it's going to be put into consideration. Scalability, again, same. Um, you might not be able to deploy, especially on large scale deployment, a single vendor. So this goes hand in hand with interoperability issues. Power consumption management. This is um, a thing in edge computing because some of them would be operating remotely on a battery, hopefully with renewable energy like solar. No? But But what if there's a typhoon that would cut your light source or power source from the sun for 3 or 4 days? Would the battery still be able to survive? So that is a huge consideration when doing remote deployment that is uh, totally isolate. Well, not technically isolated because you have connectivity, but your power, the power of your edge computing is totally self-contained. And there's the issue with maintenance and management. When these devices pops out, so who would go? Let's say if you have sensors in remote mountain, who would be the sacrificial engineer who would do that the 2-day trek to replace that battery on a sensor that was taken offline by one reason or another. So yeah, I see some labs. Most likely some telco engineers hopping through forest and mountains to install this or maintain these cell sites or some sensors. No? But yeah, I could relate. I did install a camera sensor in Taal way back 2012, I think. Yeah, because it was I was just kidnapped to help install it. And that time I was trying to figure out with Philbox, why is it a bit hot here? No? And it's the only time I realized that it was actually alert level 2 back then. And they want to install the camera so they would have a view of the crater if it's boiling or it's going to explode soon. So you could see that video from the camera we installed in Philbox with the recent Taal eruption. So that's part of the sensor network. And I was actually joking with the Philbox, so not joking. I said, sir, if the volcano erupts, would we call on the Air Force to get us? And they said that Apparently, the chopper is more expensive than us, so you just need to run fast and hopefully you don't fall into those lava pits in case it does. So, and we worked fast to install that. So again, limited computing and storage. This have considered, no? They have very limited power. They have storage, especially for those remote sensors. It needs to be computed. And with batteries, it has it has to replace some point. Did see, no, on a lot of this deployment is they would just replace the device whole, no, instead of sending an engineer with the battery and then doing it on site. They would just create and replace that equipment that fall off, and then have that equipment come back centrally, service it, replace the battery, and then use it for a different deployment. No? So, and especially if it's battery operated, no, each and every computation consumes more battery than what's needed. No? So you need to do trade-offs and balance between this. No? Like there's a huge case of edge devices where I would see arguments between the power guys and the security guys, where the security guys wants to turn on all the security features. But when the power guy is computing, no, that if you turn on AES encryption, HTTPS, the battery drain would be 30% more. Um, so they would sometimes opt again with all things considered, no, to turn off the security to gain more power, or to prolong, no, the power of these devices, no. But they have their risk analysis, hopefully, no, before they start turning off this feature and figuring out if it was really worth it to turn off the security part, no, because they need that device to run longer than intended. And hand in hand, no, security concerns, as mentioned the previous slide, no, you could turn on and off features to prolong your battery life. And but do note that these end devices, no, they contain configurations, they contain connectivity and access tokens. So consider your risk threat model where these devices get stolen and someone could dump and JTAG the hell out of that config, no? And if it wasn't properly configured or properly assessed, no, without any crypto chips or TPM chips, anyone might be able to just dump the config and get the passwords to your IoT networks, no? And you typically don't want that, and someone in choosing uh, malicious or malformed data to your environment to for whatever reason, no? Either to derail your analytics, or maybe get something or take control of infrastructure to an edge device. That is a huge possibility. So this has to be really also be factored into consideration. And again, ensuring data privacy. Again, in regards to our camera use case, you've seen cameras with SD card. That's good. Right? You have your backup storage within the camera itself. But again, what if the camera gets stolen? You got all that recording on that device, no? So we need to factor in that critical limitation. Infrastructure deployment cost, again, maintaining edge infrastructure with complex is going to be expensive and complex, especially once you factor in gateways and data centers. So you need to consider costs, no, associated with procuring, deploying, and managing edge devices. Also, of course, you need to factor in bandwidth. One of the reasons to do edge computing is to minimize latency and bandwidth, no? So you weigh, of course, always weigh the pros and cons. And on my sad story a while ago, no, a lot of people migrated to the cloud, not computing the bandwidth cost. I've seen a lot of mentioned in my intro, I was doing financial institution consulting. A lot of financial institutions move their workload to the cloud and downsize their data center, not realizing now that, well, they don't have the bandwidth and capacity, no, to have their data uh, accessed, no, by all their employees in the office. Okay, their bandwidth is not enough because used to be they were accessing it just within their data center. It's locally accessible. Now they all of them would have to cram all their traffic, no, to their limited upstream bandwidth and have all those data being brought back for processing locally. So that's a lot of factors to consider, no? And uh, Philippines, now we all know we have one of the very expensive bandwidths, no, in the region. So that didn't help, no? But we all know that we have to factor in when we're doing uh, infrastructure and deployment cost considerations. This was mentioned a while ago too, interoperability and standardization. Again, you are most likely would want to use a protocol that is used between wide range of devices, models, and even vendors. No? So you could do replacement as needed. And I'm sure some of you in electronics manufacturing have that consideration wherein you are getting this chip from this manufacturer, but it's standard. No? So in case that manufacturer weren't able to develop this or commit, no, their required number of chips delivered to you, you could contact a different vendor. Or sometimes, no, I've seen them have 3 or 4 vendors supplying the same components, no, for again supply chain resiliency in case one vendor gets burned or their factory was raided with some war or again some disaster, no, natural or otherwise man-made. You would still they could still resume operation. So we have a similar story, no, in audio, where in AK chips, no, DSP chips, no, that has known to be producing a good quality digital to analog converter chips, no. One of their plants burned down, so a lot of manufacturers recalibrated their equipment, no, to use the ESS chips, no, for replacement. But some audiophiles say that it's not the same. They still prefer the AK, but well, you cannot get AK at that time because they now have to rebuild their factory. But yeah, it's something that is going on din naman. And network connectivity, edge computing relies on the. I would argue against this. No? Some edge computing rely on stable network connectivity. No? But again, there are sensor networks that factors in unreliable network connectivity or multi-hop network connectivity, which is well also unreliable. So they might be able to store, no, their data locally to a degree and then attempt to transmit it. No? And if it fails, they will just keep it temporarily there until the network resumes and becomes more stable, and then they would be able to send out those data again. So again, most of this would have limited bandwidth. If you are on a large network, most likely your cloud computing would have high latency. Again, this would have adverse impact on edge computing performance. If at some point it's not working for your edge devices to communicate directly to the cloud, you start introducing the other components, like edge gateways, edge data center, to have intermediary in your environment. Yeah, scalability, typical for edge computing environment, you have a lot of nodes with compute power. And as you increase, no, this edge, no, edge computing must also be able to scale efficiently. Again, managing this growth, it's not only just the technical part. You also need to manage the supply chain part because you don't want to be left hanging that design a system that only works with one vendor, but what if that vendor goes out of business? No? Are you stuck and you're not able to code your changes in the environment because your contract with your developer have this very limited specs. No? So you would now need to recontract it, but you don't have the money or resource for that anymore. So again, you need to factor in scalability, interoperability, and all of these basic challenges. And this was also discussed a while ago. Power consumption and management. Again, each compute, each feature that you turn on your edge devices has its corresponding power requirements, no? So it would definitely shorten um, this the lifespan of these devices power-wise. So they need to be able to have something, no? Either something to recharge it, or uh, you would be able to compute na this edge device, assuming X number of operations, would last maybe a year, no, or two. That's about it. And then you could now schedule the replacement, or the powering off those devices if there's no other technology to recharge, especially for battery operated device. I think one of a good use case here is Apple AirTags, or tags in general. No? If you haven't seen that technology, take a look at that. It's good. It's to a degree edge computing, where I would say it's more of an edge sensor network, where you have a very small device, like this one. I put this on my keys. No? Very small device that is battery operated with CR2032, that lasts, at least Apple claims, no, 2 years on a regular operation. It doesn't have connectivity that much, no. No GPS, no GSM, only Bluetooth, low energy. That's it. It just beacons it out the ID, no, every so often. And what Apple use is, to a degree, no, the edge part would be all the Apple ecosystem, the Macs, the iPads, the iPhones. Um, when by default, basically, you are part of that sensor network. If you see a Bluetooth low energy from an AirTag, um, even though it's not yours, uh, your device would have the time and the GPS location and the connectivity to report back to Apple via GSM or Wi-Fi. No, that, hey Apple, I saw this Apple AirTag with this ID on this time, on this location, and that's it. It's sent in a secure manner. You don't even know who owns that AirTag, no, unless you scan it. Uh, but the owner of that AirTag, in case this key gets lost, they would know that when was it last seen, within the last few minutes. And they would be able to locate, oh yeah, I left my key in the office, so it's not technically lost. But suddenly your key moved, no, to some location that someone else got it. No? But yeah, it's a good tracker feature. But of course, as with any technology, it could also be used for evil purposes. No? So there are cases where AirTags has been used to stalk individuals, no? Or use it as a tracking device to individuals, which wasn't the intended use case. But Apple realizing that this technology, while good, no, could be used for something weird. uh, well, this technology could be used for something weird and evil. You might they don't want to be liable, so they added some features like if the AirTags does not see, no, their master device, iPad or iPhone, no, within um maybe 8 hours. I'm not sure the actual time. No? It is gonna beep randomly. It has a speaker, no? So that an individual that was placed with an AirTag in the car or in the bag, no, they would hear that audible thing, no, and they would start to look for it. No? There's also, this only works with iPhone. No? If the AirTag is placed with you, no, and your iPhone senses that, yeah, I've been seeing this AirTag since a few hours ago, and supposedly the master device isn't with that AirTag, it's gonna alert, no, that an AirTag is following you. Okay, so Apple imputed that kind of anti-stalking technology because they know it's going to be used for, it could be used and it's going to be used for that kind of techno. And some, let's say, individuals, no, they found that, well, if it's beeping randomly, no, and it's just technically a speaker, no, some enterprising individuals before, no, was able to disable the speaker of AirTag, and they were selling it times three the price. They call it silent AirTags. No? But again, some influencers realized that, well, I could make a lot of views with this. Upload it to YouTube. No? How do you uh, make a quiet AirTag? No? So how do you disable this speaker? So you could now Google. You don't have to pay three times the cost, which is still not expensive. No? on how to disable this speaker of air tags to make it more stealthy. But again, if you do that, it's more likely you're going to be using it not on its intended use anyway. And with that, no, degree, no, Apple's also computing the number of beeps, the number of location beacons, no, for the AirTags, and they have estimated that on a CR2032 battery, it could last for 2 years. No? Again, just by using Bluetooth Low Energy with computed number of buzz, beeps, and beacons. No? They have computed that, and they're pretty much accurate on that regards. And even that you get notified that the battery needs replacement, no? If they deem that, yeah, this device is gonna be out of powers, so you don't lose it. So yeah. Well, on that part, no, of course, you need to factor in maintenance and management too. So similarities. We got futuristic use case, no, with 5Gs, Open RAN, autonomous vehicles, no, that needs this hybrid ecosystem where you could post, process this data, or even host it, no, close to the endpoints as possible for near real-time responsiveness. Since in this regard, we have autonomous vehicles anyway. No? Last thing you want is for an autonomous vehicle, like maybe a self-driving car, no, to not have a processing power capability and have those sent out, no, to the cloud, and the cloud would decide if you're gonna turn left or gonna change lane. No, I don't want that kind of system. I want that brain to be within the car so that in case there's an issue with connectivity, but the car would be able to decide on its own. Should I change lane? Should I hit the brakes? Or on some moral dilemma, no? I would be hitting three individuals, no choice. But which individuals would I hit? One of the dilemma use cases on the self-driving car. Do you save the owner, or do you sacrifice the owner? No, on cases like that. So that's some morality dilemma that I won't delve into. um, so yeah, we got a lot of futuristic use case on why we need computing, no, on the edge devices, and why we don't want it being sent centrally to the cloud. But yeah, for let's say autonomous vehicles, some features, no, like is your car stolen? What's your speed, no, for insurance purposes, that might be sent to the cloud. Okay, but the decision for autonomous vehicles to turn left, to turn right, hit the brakes or accelerate, it has to be within that device itself. No? So that's one of our futuristic use case. Accessible automation, well, telecoms, they have been implementing this as we speak, no? Wherein, let's say, an area, no, or in a city where a tower gets taken offline, other antennas or tower within that near area, no, would maybe start trying to beam and direct beam their signal to service those individuals that lost connectivity or because the tower went out. No? So they could do beamforming, and maybe they could rearrange the antennas, no, semi-autonomously to degrade the service, no? But still have these individuals connected. No? So what would you want? A low bandwidth connectivity or no connectivity at all, right? So that's how they would make a self-healing network to a degree. So SDNs, Open RANs, and with some machine learning, no, make this automation possible. Again, we want to streamline analytics as with our use case of cameras. No, again, you don't want to just send and pop out all this data to your central storage. No? You want to streamline wherein the central storage is just receiving data on what it wants, no, to process, like maybe for biometric identification. But all the storage, all the streaming, all most of the analytics to trigger that facial recognition is already being handled by the edge and the edge gateways. Okay. Flexible pricing models, ish, but most likely this would be more on the cloud side because, well, you cannot have flexible pricing models on your edge devices that you have to purchase and deploy. Well, maybe some vendors would allow amortized cost, no? But where you buy all this equipment, but you have to pay them monthly to some degree, some subscription model. I've seen this on some IoTs, no? Where let's say you have a smart air condition controller, no? For your home or office IoT, the device is one-time purchase, no? But they might uh, have a pay-as-you-use feature where if you pay, let's say, 1,500 pesos a year, no, you would have a feature to store, no, all your data for a year. Then your temperature data, your humidity data. Then you could have some AI, machine learning, buzzwords, analytics where it could sense the temperature and pollution outside and have your aircon, no, adjust accordingly. Um, so yeah, you got those type of pricing models, and typically that's how IoT vendors would make money because they don't want a single purchase device that maybe a device that's very robust gonna last 10 years, no? And diba, at some point, all people would have these devices na, that would want to acquire it, have these devices, and they would be left out without any revenue. So that's their sort of, they're gonna have recurring revenue even if you have that device already purchased for you, with some features that they are keeping it on a paywall. Hassle-free regulatory compliance. So a lot of these vendors setting up clouds and edge computing centers worldwide, they want to ensure regulatory compliance, no, within all jurisdictions. So this goes hand in hand, no, with cloud um, and edge computing. That maybe some financial data or government data that you don't want to be hosted, no, on different jurisdiction, different country, which no, no, which is being challenged actually currently right now. So the war in Ukraine made the point on government cloud systems, wherein they are still able to operate at this point, no, because when they were in annexed during the 2014s by Crimea was annexed by Russia, no, they started a move, no, of their government systems to the cloud, AWS specifically. And when they have invasion, basically, of course, the telecoms would be a target. They are still able to operate, no? Because even without their data center operating onshore, all their government system is in AWS anyway, and they think that it's not gonna get attacked anytime soon, so they could still operate with their government e-government systems. So, but they have to write a law most likely that would allow them to host their uh, government data on a different political jurisdiction. So differences. Again, basic difference is where would the computation takes place. For cloud computing, it's in the cloud. For edge computing, it's most likely gonna be on the device, okay, or on the edge gateways and server. No, it's somewhere near the device. That's the difference, basically. Speed and agility. Edge computing, they could compute and process that data faster. Well, depends really on their compute capacity still, no? But if you are streamlining your process, can get some detections or you just want some responsiveness. Let's say you are in operational technology, no, and one of the pipes pressure is spiking and you need to shut it down. Last thing you want is have that device transmit that data centrally in the cloud, and the cloud decide to, okay, that's dangerous, you need to shut it down. But by then it's too late. No, maybe uh, your network connectivity cable was burned out with that pressure cooling. So the command to shut down that or release open the release valve did not push through. Hence, you have now a disaster on your side. So again, speed and agility is factor of edge computing, but that's speed and agility on the decision itself on the device, near the device. You also have technically speed and agility in the cloud, but this mainly pertains to deployment. You have on-demand scaling. pay as you use. You're very agile. No? You don't have to wait for vendors to do the whole procurement dance wherein you need to get a quote. You beg for discounts. They agree, and then they deliver, and then it gets delayed. Then once your equipment gets delivered, you have to deploy, and then you realize you don't have the power capacity and space. But you don't have that in cloud computing. You have very good speed and agility in deploying, but not in processing, especially if you need near real time response. Yeah, particularly performance, your resource again are placed close proximity to the end users. So the performance, the responsiveness within a few milliseconds. No, you could make it even microseconds depending on your compute requirements. No, but in cloud computing, it's basically again you don't need to purchase all this equipment. No, but for to increase your performance and productivity, you could just auto scale, no? And just pay as you use. Don't have that issue with your traditional data center, physical data center requirements. So, sample for productivity and performance. No? We have here um, neural engine, no? Apple's neural engine peak throughput, and this is just on the iPhone 13 Pro. No? We're now on the iPhone 15, wherein they could perform machine learning on the device itself. And this allows, no, if you go to, let's say, your photos, you could easily search there, no, beach photos, no? And that device will give out photos of what looks like a beach. And for the most part, it's actually very good at searching. It even has a built-in text, image to text. So if you're searching a document, diba, you could, it's not, and it's all auto OCR when you take a picture of that, no? And you could do search for it. And again, with the iPhone 13 Pro, you have 15.8 teraflops on it. And I'm sure the 15 Pro would have much more compute capacity for neural engine processing. And they're actually now trying to put large language models on the device itself. No? That would make machine learning a bit more close to the end devices, or not close, it's within those edge devices pretty soon. They don't have to send it back to the cloud. And sample, let's say for uh, Apple Apple Watch Ultra, no? Used to be the Siri assistants, no? They would record your voice, send it to the cloud, process it there with voice recognition, check out what you're trying to do, and then once it converts it to an actual instruction, sends it back to the device, and the device will do it. So you need connectivity, no? With the upgrade for Apple Ultra 2, they said that now it has Siri on device. So it could the voice processing is handled on the device itself, and they don't need cloud connectivity for you to use Siri, which is good, no? Especially if you're on a very spotty network connectivity. You could have your own Siri contained within that small watch. It's a good technology, actually. It's a form of edge computing. So scalability, yeah, you need to account for device heterogeneity in edge computing because again, you'll have interoperability issues, no? And hopefully you have figured that out before deploying or committing to various vendors. And with these edge devices, they are usually operating in dynamic conditions as compared to climate-controlled cloud computers. These edge devices might be deployed on forests, on mountains with varying degrees of temperature, maybe on oil platforms, no, in the sea that's very high humidity, or maybe in the desert that's skyrocketing temperatures. No? So your device should be able to perform on that kinds of condition, or if you intend to deploy it on that condition, of course. Again, with cloud computing, typically easy for scalability, and supposedly you have zero downtime. No? But you all know that's not true. No? We got a lot of cases where there are AWS outages, Microsoft being DDoS, Google Cloud has some misconfiguration issue. No? So it's really There are still issues with cloud computing, but I assure you that the uptime of cloud computing is definitely a lot better than the uptime of your on-prem data centers. No? So I'd like to see someone challenge that. Also reliability. Again, edge computing, especially if you are configured a multi-hop network. If a node fails, you should be able to figure out your path outside and connect to the network. So losing a few nodes should not affect users now from accessing the service at total efficiency. They should be able to reconfigure themselves. That comes hand in hand with edge computing protocols, no, or ad hoc network reconfiguration. For cloud computing, well, it's more reliable because you are in a controlled environment. No? You got cooling, you got cool power, very stable power. You got typically these data centers are located on areas that's not prone to natural disasters. They got good fiber connectivity. They got maybe backup satellites. And these are basically data centers anyway. No? So they have large gensets with huge capacity of fuel, no? In case anything goes wrong with the local grid, they would be able to continue operations. No? So reliability is more leaning towards cloud computing than edge. But when you deploy edge, you need to factor in, of course, the reliability part. And for security, edge computing is I would say on the losing end here because, well, again, your devices could be stolen. And if the keys, the tokens, and the configurations and the connectivity is within that device and it's not properly secured and encrypted, anyone could, again, extract that via JTAG or maybe as bad as popping up the SD card, no, and mounting it on your threat actor's laptop, then they could see everything. It's an issue. It has to be considered on threat modeling. In cloud computing, that's not a problem because, well, there has been very few cases of cloud environment being breached through the cloud provider itself. It's most likely because of a misconfiguration of the user. No? They got very poor password hygiene. They have web application that they thought that the cloud's gonna be protected against this attack, not realizing that, well, cloud is a shared responsibility. No? So the web vulnerability is the user's responsibility. So it's not the fault of the cloud. So that's typical issue where these breaches in the cloud environment comes into play. Or maybe it's a very complex password, no, but the admin got phished. It thought it's logging to an AWS dashboard, but it was a phishing site. So even with the OTP, no, again, even with OTP, it's a lot better than username and password alone. But SMS and authenticator-based OTP is just one step more, no? And it could be still it could still be phished. It's not a silver bullet. So put that into consideration. Okay, so I think that's the last one for our course. So we have some key learning points here.